Hello, everybody. All right, so um, we were talking in the last lecture about brightness, magnitudes, luminosity, um, and before we go deeper, we do need to take a few minutes to take a half a step back and talk about some basic physics of light and what light is and how light works. Um, because once telescopes and physics was invented, I was going to say like astronomy goes back thousands of years, right? Astronomy goes back to, well, I mean, prehistory of people looking up at the night sky and seeing stars and planets and the moon and whatnot, and making up names of stars and constellations and all that, right? So astronomy is ancient. Physics, at least in the form that we think of it today, was organized, invented in the 1600s with people like Galileo and Newton. And so once you start having the basic tools of physics to start analyzing astronomy, you can really discover some really powerful stuff. And so let's do a quick treatment, and I'll try not to belabor the point because you've already seen most of this in the homework, but I think it's worth saying twice to hopefully hammer it into your head. About the properties of light, the nature of light, so that when we jump back into astronomy in a few minutes, we can use what we know about how light works to figure out why and how objects emit the light that we see. Right? If you don't know how light works, then you're looking up at the sky or you're, pointing your telescope and you're taking pretty pictures. You're stargazing, which is fun and that's fine. But if you want to really figure out some real answers, if you want to figure out how things work, then we need to understand what information we can get from the light that we're receiving. All right, so let's do a quick review of what light is and how it works, and then we'll go back into how we can get information out of that light from stars and other objects. Okay? So before we get into light, though, we need to go even more basic and talk about how in nature there are four fundamental forces. Every force of nature is an expression of one of the four basic forces. Gravity is one of them, so we're probably familiar with that one. Another is electromagnetism. So electricity and magnetism are the same force. They're the same phenomenon. And electricity and magnetism both arise from electric charge. So we're getting real basic here. We're getting really like, okay, at the fundamental level of reality, particles in nature have this property that we call electric charge. And some particles have a positive charge. What kinds of particles? Give me an example of a particle that has a positive charge. Like protons have a positive charge. Some particles have a negative charge, like electrons. Okay? And because these particles have a charge, they create an electric field around them. And usually we denote this when you draw a diagram, when you draw an electric field diagram, by convention. We've said, okay, so the field created by a positive charge will point away from the charge, and the field around a negative charge will point toward the charge. It's sort of a convention that we've come up with for how we draw these things, because it's useful. When two charged particles come near each other, their electric fields interact. And when electric fields interact, that gives rise to the electric force. So when you place a positive charge and a negative charge near each other, their electric fields link up. And that, when they link up, that gives rise to the electric force that attracts those two charges together. Those two charges get pulled together. So to review here for a second, right? The electric charge creates the electric field, and when their electric fields interact, that creates the electric force that attracts opposite charges. When you put two charges that have the same sign, either both positive or both negative, when you put those near each other, their electric fields interact by basically bumping up against each other and pushing each other apart. And since the electric fields are pushing each other apart, that creates the electric force that pushes the charges apart. So that's why when you have two positive or two negative charges, those charges repel each other. So, if I take a charged particle, and in this case, let's take an electron, because electrons are common and low mass, so they're easy to play with, they're easy to manipulate. If I take an electron, and that electron is going to create an electric field like this, but if I grab onto that electron, and if I start jiggling it up and down, if I start oscillating the electron, the moving of the electron is going to create ripples in the electric field. And those ripples are going to radiate outward like ripples in a pond. What do we call those ripples in a pond? Waves. So basically, by grabbing onto this electron and jiggling it up and down, I'm creating waves in the electric and magnetic fields that are created by the charged particle, by the electron. So I have created an electromagnetic wave. I have created a wave in the electric and magnetic fields. And that's what light is. Light is a wave made of, light waves are waves of electric and magnetic fields. And so light waves behave much like any wave, right? But there's one big exemption? No, what am I trying to say? There's something that's very special about light waves, which is that other kinds of waves, like water waves and sound waves, they need a medium, they need a material to be oscillated in order to create the wave, right? In a water wave, it's the water that's moving up and down. In sound waves, it's air that is vibrating back and forth, right? So you can't have water waves without water. You can't have sound waves without air. Light, though, is special in that, what are light waves made of? They're made of electric and magnetic fields. And electric and magnetic fields can exist in empty space. Essentially, a light wave is made of space. It's made of the fields that are carried by empty space itself. And so because these electric fields, like here and here, these electric fields, they're part of space itself. They can exist in empty space. And since you can have an electric field in empty space, light can travel through empty space. You don't need a medium to carry the wave, because the light wave essentially carries itself by traveling with the electric fields that it's made of. Right? The light wave travels by having that electric field vibrate up and down and so on as that light wave ripples through space. And so the properties of a light wave are basically the properties of any wave, a sound wave, a water wave. But, let's not complicate things. Let's just focus on light waves here, right? there are three basic properties of any wave, like a light wave, one of which is the wavelength, right? The wavelength is just the distance from one wave to the next. The frequency is the number of waves that happen per second, so the number of oscillations that happen per second. And then there's the speed, right? The speed is just how fast the wave travels through space. And with any wave, those three properties are related to each other by this equation, that the speed of the wave is equal to the wavelength times the frequency. Think about this for a second, right? This hopefully should make a little bit of intuitive sense, right? If you take the size of each wave, or you take the distance per wave times the number of waves per second, and that tells you how far per second the wave will travel, the speed. Now, the special thing about light is that light always travels at the same speed. Light always travels at the speed of light. We're going to get into this more later in the semester, but the speed of light is one of those fundamental constants of the universe. Right after the Big Bang, a tiny fraction of a second after the Big Bang, the universe made some basic decisions. Things started to settle down. And the first thing that kind of got settled right after the Big Bang was, what are the values of the fundamental constants, right? And those fundamental, there's a handful of fundamental numbers that describe and define the universe that we live in. One of them is the speed of light, right? Because why? Because light travels through empty space. And so empty space is basically the same everywhere in the universe, so therefore light travels at the same speed everywhere in the universe. Some of the other fundamental constants are things like gravity, right? The constant that defines how strong gravity is in this universe, and there's a handful of other ones. So, because the speed of light is always the same, because the speed of light is a constant, this number doesn't change. What that means, though, is that wavelength and frequency are inversely proportional. If the wavelength goes up, the frequency goes down. If the frequency goes up, the wavelength goes down. If one goes up, the other one has to go down, so that wavelength times frequency always equals the same speed. Okay? Now, when light goes in your eye, we don't see it like this, right? It's not like light goes in your eye and what your eye sees is like, oh yeah, rippling magnetic field, electric field, both. Why? Why do we see light the way that we see it? And the answer is because the wavelengths are way too small. How do we see light? How do our eyes and our brain perceive light? How do we talk about different kinds of light? We talk about them in terms of colors. Color is just light of different wavelengths, where the visible spectrum, the light that we can see with our eyes, goes from, red, orange, yellow, green, blue, violet, right? Across the spectrum, the visible spectrum, where the reddest light that you can see, red light, is the longest wavelength and therefore the lowest frequency. Because remember, wavelength and frequency are inversely related. So long wavelength means low frequency. And then as you go across the rainbow, the waves are getting shorter and shorter and shorter, but if the waves are getting smaller, then the frequency is getting higher, until you get to the violet end of the spectrum, which is the shortest wavelength and the highest frequency light that our eyes are sensitive to. Now, what kinds of wavelengths are we talking about here? All right, so our eyes are sensitive. Our eyes can detect light of wavelengths between 400 and 700 nanometers. I'm using nice, easy numbers here because, of course, biology is complicated and everybody's eyes are a little bit different, right? Some people can only see light down to 650 nanometers. Some people have really good eyes and can see light of 720, 715, things like that, right? And, so different people have slightly different eyes, and also your eyes change sensitivity as you age. So, just if you want nice round numbers, and who doesn't, then the reddest light you can see is about 700 nanometers, down to the most violet light you can see, which is about 400 nanometers. What is a nanometer? Right? A nanometer is a billionth of a meter. Right? Because remember, what is wavelength? Wavelength is a length. It is the distance from one wave to the next. So you measure, in SI units, right? In basic physics units, you would measure any length in meters. But of course, you wouldn't want to measure the wavelength of visible light in meters, because it would be like 5 times 10 to the negative 7 meters, which becomes annoying at some point. So we're just going to use a metric prefix here. We're going to say nanometers. So the light that we can see is a few hundred nanometers, a few hundred billionths of a meter. And that is why when light goes in your eye, you don't see the wave, because the distance from one wave to the next is a few hundred billionths of a meter, which is way too small for our eyes to see. And therefore, when light goes in your eye, it's not like your eye is actually measuring the wavelength. It's just that the cells in your eye absorb light, and then they react, right? A ray of light goes in your eye, and the cells in your retina absorb that light, and they react, and they go, aha, I recognize that wavelength, I call it blue. And then your eye tells your brain, I'm seeing blue light. And then another ray of light comes in your eye, and the cells in your eye react and go, aha, I recognize that wavelength, I call it red. And then your eye tells your brain, you see red. There are lots of other wavelengths of light, though. There are light waves of all conceivable wavelengths, from the very long to the very short. This sliver of the spectrum, this is just the range of wavelengths that our eyes react to. This is the range of wavelengths that our eyes evolved to be sensitive to. There is longer wavelength light than red light, right? That's the infrared. And then even longer wavelength than infrared is the radio waves. So radio waves are the longest wavelength and the lowest frequency light. There is shorter wavelength light than violet, which is why it's called ultraviolet, because it's literally more violet than violet. And then even shorter wavelength is the X-rays, and the shortest wavelength light is the gamma rays, and therefore short wavelength means high frequency. So the highest frequency, shortest wavelength light is the gamma rays. It's all the same stuff, right? All of these different kinds of light are still light. They're still just electromagnetic waves. It's just waves of different wavelengths and frequencies. Okay? For future reference, I said before, what is frequency? Frequency is the number of waves per second. So you could measure the frequency of light in waves per second, although that becomes a little bit of a tongue twister at some point. And so at some point, probably in the 1800s, 19th century, when they started measuring frequencies of waves and such, they shortened that to the hertz. So 1 hertz is the SI unit for frequency, where 1 hertz is a frequency of 1 wave per second. Okay. All these different kinds of light, red light, green light, ultraviolet, infrared, they're all just light of different wavelengths and different frequencies, but they all travel at the same speed, right? All light traveling through empty space travels at the same speed, regardless of wavelength or frequency. Right? Because that's a fundamental constant that is baked into the universe we live in. And that speed of light is 3 times 10 to the 8 meters per second, Or in the homework, sometimes you'll measure it in kilometers per second. And so it's 3 times 10 to the 5 kilometers per second. Right? There's one other property of light that's important, and that is that, like the homework talks about, right? Light waves are broken up into these packets. Light waves are broken up into chunks called photons. So you can kind of think about a photon as being like a particle of light, although it's not quite a particle like a proton is a particle. It is a packet of waves. And the energy, as it turns out, the energy that a photon carries, the energy that a packet of light waves carries, only depends on the frequency. This is a common mistake people make. So let's think about this for a second. The energy that a photon of light carries does not depend on speed, because all light travels at the same speed. But light particles, photons, carry a different amount of energy depending on the frequency. So the energy in this equation, the energy is the energy of a single photon, which is equal to h, which is another constant called Planck's constant. Again, this is another constant of nature, so it's not a variable, it's just a constant. The only variable here is the frequency. Right? The higher the frequency, the higher the energy. The higher the frequency of a photon, the more energy it carries. Okay? All right, so a few questions. What do you think? Which of these kinds of light is not a form of light? Oh, I just gave it away, didn't I? Which of these is not a form of light? Radio waves, X-rays, ultraviolet, or they're all light, or none of them is light? I gave it away, didn't I? It's D, right? They're all light, right? Just because it's not visible, right? Our eyes can't see radio waves, X-rays, or ultraviolet, but they're still light. They're still made of electromagnetic waves, even if it's just not visible to our human eyes. I'm assuming we're all human. I don't know. Maybe I'll save these videos and I'll still be using them in many years. Once some of my students are aliens or robots. Maybe I drank too much coffee this morning. Anyway, next question. Which of these kinds of light has the shortest wavelength? I'll let you consult your notes. All right. Might be good for you to write down in your notes what the list of kinds of light is from shortest to longest wavelength, or from lowest to highest frequency, whichever you want to do it. Because if you remember, right, the full electromagnetic spectrum, which one has the shortest wavelength? That's, of these four, X-rays. Yes, gamma rays have even shorter wavelength than that, but that's not one of your options. So be it is. Which of these has the lowest frequency? Well, low frequency means long wavelength. So what kind of light has the longest wavelength? That's the radio waves. So A it is. Which of these has the highest energy? Well, the energy of light comes from its frequency. High frequency means high energy. So this question could also be asking, which of these kinds of light has the highest frequency? And the highest frequency of these is X-rays again. So B it is. Answer is, they all travel at the same speed, right? They all travel at the same speed because they're all light, and all light travels at 3 times 10 to the 8 meters per second. Yeah, D it is. Okay, couldn't put it past you. Okay, so that's light in general. Okay, now let's talk about how objects give off light. You can learn a lot about an object in the universe, not just by looking at it either with your eye or in your telescope, but one thing that Newton, I think, was the first person, Isaac Newton was the first person to realize, if you take the light from an object, like, say, the sun, which is what Newton was experimenting with, you take light from the sun, you shine it through a prism. When you shine that light through a prism, it breaks the light up into the rainbow. Right? You take all of the light from an object and you shine it through a prism and you split the light up into the different wavelengths. You split the light up into the different colors, into the different constituent wavelengths to create what's called a spectrum. So the spectrum of an object is where you take all the light coming at you from that object and you split it up into the different colors. Because that way you can look at the colors individually. Now what are you doing? Now you're slicing and dicing the light to look at, well, how much red light am I getting? How much orange light? How much yellow light? How much green light? How much light are you getting of the different wavelengths? Which can give you a lot more detailed information. Okay? So, there are 3 basic types of spectra that objects in the universe give off. The first kind is what's called a continuous spectrum or a blackbody spectrum. It's called a blackbody spectrum for historical reasons that I'll spare you. We'll talk about spectra 2 and 3 a little later, but today let's focus on just number 1, the continuous spectrum or a blackbody spectrum. A blackbody spectrum is what you get from a hot, dense object. Right? Because if you've got a hot, dense object, if it's hot and it's dense, well, if this object is hot, that means all of the atoms and particles are moving around, jiggling around, vibrating in your object. And if the object is dense, that means all of those atoms are packed in really tightly together. So they're constantly running into each other, right? These atoms are packed in tightly, they're vibrating, they're constantly running into each other like a really complicated big game of billiards or something, where there's just collisions and collisions and collisions over and over again. And so when you have a dense object where these atoms are colliding fast and furious, what you get is some of those atoms statistically, this is a game of statistics, where just statistically, some of those atoms are going to be moving real slow, and some of the atoms are going to be moving real fast, and most of the atoms will be moving somewhere in the middle. And well, when those atoms give off light, the atoms that have very little energy can only give off a low-energy photon. Now, a low-energy photon, here's the quiz, low-energy photon means long wavelength or short wavelength? Low energy means low frequency, means long wavelength. So there's going to be a few atoms that have very little energy and therefore they only give off low-energy, long wavelength light. And there's going to be a few atoms that are moving really, really fast, and they have a lot of energy, and they can emit high-energy photons, right? So these photons have a lot of energy. They're very short wavelength, but there aren't that many atoms that are that hot. There aren't that many atoms that are that fast. So you only get a little bit of short wavelength light. And most of the atoms are moving somewhere in between, right? Most of the atoms are moving with some average speed, and therefore most of the atoms give off light that is somewhere in the middle. I really think about a game of billiards like this, right? If you're starting a game of billiards and you've got the balls racked and then you've got absolutely no skill, you just absolutely whack the cue ball and it slams right into your triangle of balls and the balls just go flying everywhere, right? If you watch those balls scatter, a couple of those balls will be shooting off real fast. And a couple of the balls will be rolling away real slow, but most of the balls will be moving with some speed somewhere in the middle. It's a game of statistics. And therefore, if you look at the spectrum of light, if you take the light given off by a hot, dense object, you split the light up through a prism, you look at the rainbow, you look at the spectrum of that object, you're going to get a little bit of short wavelength light and a little bit of long wavelength light, but the object is going to be brightest somewhere in the middle. This is what you call a continuous spectrum, or a blackbody spectrum, or a thermal spectrum. 3 names for the exact same thing. But what do you get, right? From this continuous spectrum, from this blackbody spectrum, you always get this object gives off all the colors of the spectrum. This object emits all the colors, but not with equal intensity. It's brightest somewhere in the middle. And here's why this is also called a thermal spectrum, because it depends on temperature. Here's the awesome thing about a blackbody spectrum. It only depends on temperature. It doesn't actually depend on what the object is made of. Notice I just said you get a blackbody spectrum from a hot, dense object where those atoms are packed in tightly and they're moving real fast. It doesn't actually matter what kind of atoms you're talking about. It doesn't depend on composition. It just depends on temperature. So let's look at a star, because a star, the core of a star is hot and dense. So the core of a star gives off a continuous spectrum. So let's say you look at a 3000 Kelvin star. Now, 3000 Kelvin sounds really hot, but stars are very hot. So 3000 Kelvin is pretty cool by star standards. So that star, the red curve here, it gives off a little bit of short wavelength light, a little bit of long wavelength light, but it's brightest right here at about 1,000 nanometers. If I take that star and if I crank up the thermostat and I heat it up to 5,800 Kelvin, like the surface of the sun, then notice what happens from the red curve to the yellow curve. The curve moves upward. Now, what is the vertical axis here? Intensity. So when I say the curve moves upward, what I mean is the star is giving off light more intensely. If the star is more intense, how does it look? It's going to look brighter. So by heating up this star, the star gets brighter at all wavelengths. The curve moves upward at all wavelengths. So the star is getting brighter at all colors. But also notice what happens to the peak. The peak, oh, my mouse is getting stuck. Sorry guys. The peak was here, now it's shifted over here. Now it's shifted to being right in the middle of the visible spectrum. This, by the way, this is why our eyes evolved to see this part of the spectrum, right? Our eyes, it's not an accident. Our eyes evolved to be sensitive to this part of the electromagnetic spectrum because that's where the sun is brightest, right? That's where the sun illuminates the earth most intensely. So what happened? By heating the star up from 3000 to 5800 Kelvin, the star has gotten brighter, but it's also preferentially brighter at shorter wavelengths. And shorter wavelength light is what color? What color is the short wavelength light? It's blue and violet. So this star has gotten brighter. By heating it up, the star has gotten brighter, but it's also gotten bluer. And when I say bluer, I mean giving off more short wavelength light at all wavelengths. If I take this star like the sun and I crank it up all the way to 15,000 Kelvin, now we're getting into a pretty darn bright star. Notice the same thing happens. The star gets brighter at all wavelengths, but also the peak has shifted to even shorter, even bluer wavelengths. It's all the way over here now. So that's what happens to a star or any black body, not just a star, any hot dense object, as you heat it up, it gets brighter, it glows brighter, and it glows bluer. Why bluer? Because it is preferentially giving off more short wavelength, more blue light. And that is something you can see in your telescope. Because like I said, the shape of this curve, the shape of the blackbody curve, only depends on temperature. So where the peak in the spectrum is, whether that star is brightest here, or here, or here, or here, or here, or here, like your body, right? Your body is warm and dense. Human body temperature is about 310 Kelvin. So your body is giving off light. But, you know, we're not hot like a star, we're just warm like a body, and therefore the peak in your body's blackbody spectrum, the peak in your body's continuous spectrum, is right over here. What part of the spectrum is this? This is in the infrared. You can't see infrared light with the naked eye, but how do we detect infrared light? How does our body sense? How does our body detect infrared light? It's heat, right? Our eyes can't see infrared light, but the nerve endings in your skin, absorb infrared, and they tell that to your brain, and we perceive that, our brains perceive that as heat, right? So that's what body heat is. Your body heat is just your body giving off its infrared light, which then you can feel as heat, right? So this is a second measurement. Sorry, this is a third measurement we can make, right? Because if you look at a star, take the light from that star, shine it through a prism, break the light up into the rainbow, and then if you go and measure, how much red light am I getting? How much orange light? How much yellow light? How much green light? How much blue light? How much violet? If you take the light from that star and graph intensity versus wavelength, and you say, aha, that star is brightest at this wavelength, you can figure out what the temperature is. You don't have to go get in a spaceship and fly up to a star and stick a thermometer in it to figure out what the temperature is, because that would be very hard to do. We don't have to. The relationship between the temperature of a blackbody and the wavelength of its peak is given by this equation. This equation is what's called Wien's displacement law, or just Wien's law, where the wavelength of the peak in the spectrum, the wavelength at which that object is brightest, only depends on temperature, where the peak wavelength equals 2.9 times 10 to the 6 nanometers times Kelvin. So these are just units. Nanometers times Kelvin divided by the temperature in Kelvin. So now all you've got to do is measure the peak wavelength, plug it in here, solve for temperature, and now you know the temperature of that star. Even if that star is 1,000 parsecs, 1,000,000 parsecs, even if that star is impossibly far away, if you can see the star, you can see the spectrum, you can measure the peak wavelength. This is one of those measurables that will tell us something real and physical about the star. We know how hot the star is. This is another equation. This is another formula to put in your spreadsheet, because we're able to figure out the temperature of the star now. All right, what do you think? A 15,000 Kelvin star is brightest at which part of the spectrum? Well, this 15,000 Kelvin star has a blackbody curve like this, so it's brightest here at this wavelength. What kind of light is this? Ultraviolet. A 15,000 Kelvin star is brightest in the ultraviolet spectrum. What's the true visual color of the sun? Well, I was going to say, if you look at the sun, okay, don't look directly at the sun, right? Bad idea. This is what we see, right? Our eyes can only see this part of the sun spectrum. So what are we seeing? When you look at the sun is pretty much a flat. It flattens out right here, right? This star, let's look at the 15,000 Kelvin star. This 15,000 Kelvin star is brighter in the blue and fainter in the red. So if you look at a 15,000 Kelvin star, what color does it look? It's this 15,000 Kelvin star is giving off all the colors of the rainbow, because every black body gives off all the colors of the rainbow. But it's brightest in the blue, so you look at this hot star and it's going to look blue to the naked eye. Look at the 3,000 Kelvin star. This 3,000 Kelvin star is giving off all the colors of the rainbow, but it's brightest in the red, so if you look at a 3,000 Kelvin star with the naked eye, it's going to look red. Right? You can just look at a star with the naked eye and you can get a pretty decent sense of its temperature. The hotter means bluer, cooler means redder. It's basically the opposite of your sink faucets, right? In astronomy, blue means hot and red means cool. That's a good thing to remember for later. But what about the sun? The sun is giving off all the colors of the rainbow with pretty much equal intensity. So what color do you get? What color do you get when you have all the colors with equal brightness? It's white. The sun is white. Which might throw you off for a second, because you think, well, wait. I don't typically think of the sun as being white. When you look toward the sun, it usually looks yellow. Why does the sun look yellow? And the answer is because there's something in between the sun and your eye. The atmosphere. Right? The atmosphere, the Earth's atmosphere scatters some of that sunlight. And the sun, you know what? Let me zoom in here. I'm gonna be real basic about this here real fast. If we zoom in here, right, our atmosphere is really good at scattering blue light, right? That's why the sky is blue, right? The sky is blue because sunlight hits the atmosphere, and Earth's atmosphere scatters the blue light in all directions, but the yellow light, the green light, the red light, that has an easy time getting to your eye. So if there was no atmosphere, then we would see all the colors just fine and the sun would look white. But because the atmosphere removes some of the blue light, what we see to our eye is the yellow, the green, the red, so the sun looks red. Sorry, yellow. The sun looks yellow from here on Earth. How do I know? How do I know that if you get rid of the atmosphere, the sun will look white? Because that's what we saw when the Apollo astronauts went to the moon, right? The photos that the Apollo astronauts took from the moon, there's no atmosphere on the moon. There's no atmosphere on the moon, and therefore what you see on the moon is that the sun does look white. How about this? Which of these objects is hotter? Well, this object is peaking at the violet. This object is peaking in the red. So which of those objects is hotter? The object that's hotter is going to have its peak at longer wavelength or shorter wavelength? Shorter wavelength. So A must be hotter. There's one more thing we can do with this. Because with a graph like this, what are we seeing? We're seeing a graph of intensity per square meter per second versus wavelength. So if you have a graph like this, you can get a sense of the luminosity, because What this graph is this is a graph of energy emitted at each wavelength. So if you take the full area under the curve, if you take the full area under each of these curves, you're adding up all of the light at all the wavelengths, and you're saying, well, what's the total amount of energy that this star gives off at all wavelengths per second? That's the luminosity. So, like we said before, hotter stars tend to be brighter. Cooler stars tend to be fainter because they're giving off less light at all wavelengths. So you can take the area under the curve and get a sense of the luminosity. The greater the area under the curve, the brighter the star must be in total. So look at this. Which of these objects is brightest? Well, the brightest, the highest luminosity star must be the one whose graph has the greatest area under the curve. Which of these has the greatest area under the curve? Sure looks like this one. And you think, okay, this has a pretty high graph. This is a pretty high peak. This must be the brightest star. And you'd be right, except also what's happening? The wavelength peak, the peak of the wavelength is in the red. If object D here, object D is the brightest. It's got the greatest area under the curve. What's going on here? This star it's peaking in the red. Red means what? Red means cool. So this star is bright, it's the brightest, even though it's cool. It's cool in red. How can that be? Well, it turns out that the luminosity of a star doesn't just depend on temperature, it also depends on the size. A star can be high luminosity because it's hot, or because it's large, or both. This is the full physics equation. The full luminosity of a star in watts is 4 pi times the radius of the star squared. Now, 4 pi r squared. 4 pi r squared should hopefully ring a little bit of a distant bell in your head. 4 pi times the radius squared is the formula for the surface area of a sphere. Right? When we talk about the radius of a star, what we really care about is surface area. Because if that star has a greater surface area, then it's got more surface to let the light out. And if the star has more surface to let the light out, more light is going to escape per second. And if that star lets out more light per second, that's higher luminosity. So the luminosity of a star depends on its surface area and the temperature of the surface. All of this is multiplied. Now this is, again, radius squared. Temperature to the 4th power. This is huge, right? If you double the temperature of a star, if you double the temperature, that doubled the temperature gets raised to the 4th power. What's 2 to the 4th power? 2 to the 4th power is 16. So that all you've got to do is double the temperature of a star, and you've increased the luminosity 16 times. So this is why hot stars are so much brighter. And this is why cool stars are really, really dim. If you go out tonight with the naked eye, hopefully it's a nice clear night, go out, look at the stars. Do you see more bluer stars or more reddish stars? Most of the stars that your eye can pick up with the naked eye are the bluer stars. Because bluer stars are more common? Not really. It's just because blue means what? Blue means hot, and hot means high luminosity. Those bright bluish stars that you can see in the sky with the naked eye, it's not that those blue stars are terribly common. They're actually kind of rare for reasons that we're going to get into in a few days. But It's just that those blue stars are so much higher luminosity, they're bright enough that you can see them with the naked eye. There's a lot of cool red stars that are pretty close to us in the galaxy. But red means cool, low temperature, and low temperature tends to mean low luminosity. And therefore, they're so faint that it's really hard for your eyes to see them without binoculars or a telescope to help you out. Which means those few red stars that you can see, Betelgeuse, Aldebaran, right? The red stars that you can see with the naked eye, how can you see them? Why are they so low luminosity? That's the question about object D. How can object D be so bright if it's so cool and red? And the answer must be because it's huge. Right? Object D has such a high luminosity because it's not very hot. It's not very hot because it's red, but it has such a large radius. It's so big that it still has a large luminosity. It's getting its object D and Betelgeuse and Aldebaran. This is why these stars are called red giants and red supergiants, right? Red supergiants have insanely high luminosities even though they're not very hot. They're getting all their luminosity from their radius, not from the temperature. Okay, so the luminosity of a star depends on radius and temperature. The rest of these are just constants, right? 4 pi, you know what pi is. Sigma here, the little lowercase sigma, is it's what's called the Stefan-Boltzmann constant. It's another constant. And if you were doing this equation using SI units, the Stefan-Boltzmann constant has a value of 5.67 times 10 to the negative 8 watts per square meter per Kelvin to the fourth. Again, because you're doing this equation is all in SI units where the luminosity is in watts, the radius of the star is in meters, and the temperature is in Kelvin. Wow, that seems like a lot of work, especially when you're talking about stars where the luminosity in watts is a huge number, the radius of a star in meters is a huge number. Temperature's not that bad, it's just a few thousand, right? But this, and then you got to like juggle the Stefan-Boltzmann constant putting in there. This becomes, not hard in SI units, but, a little bit of extra work there, typing in the scientific notation in your calculator. Why don't we rearrange this equation using solar units? Instead of talking about luminosity in watts, let's talk about luminosity in solar luminosities. That'll make the math easy. Instead of measuring the radius of this star in meters, let's measure it in solar radii, in radii of the sun, like we did in that first lecture. That'll keep the numbers nice. Here's the awesome thing. We know that for any blackbody, for any spherical blackbody like a star, this equation is going to be true. We already know how to get the luminosity. You can figure out the luminosity from the absolute magnitude. Now we know how to get the temperature because you use the peak wavelength. Use Wien's law to get the temperature, which means now we can actually figure out how big the star is. You can't look at a star and see how big it is, right? You look at a star with the naked eye. What does it look like? It looks like a point of light in the sky. You look at a star in a telescope. A star just looks like a point of light in a telescope. Stars are huge, right? But stars are also so far away that the size of a star is smaller than the resolution limit of your telescope, right? You can't resolve the size of a star in a telescope. They're too small. They just look like pinpoints of light, even in a telescope. I mean, there's one star that you can actually see the size of, right? The sun, because it's right next door. Every other star, you can't just look at a star and say, oh no, that's clearly 3 solar radii. No, they just look like pinpoints of light. But if you can measure the luminosity, which we can, and if you can measure the temperature, which we can, then we can solve for the third thing. We can solve for the radius. And here, I've done the job of making life a little easier for you. Here's the formula to solve for R. The radius of this star in solar radii is equal to the square root of luminosity in solar luminosities divided by the temperature over 5800, and that's temperature still in Kelvin here. So the temperature in Kelvin over 5800 squared. Use the magnitude to get the luminosity, use the color, use the peak wavelength to get the temperature, and now you can figure out whether some stars are big and some stars are small, which is pretty awesome. Now we know which stars are the dwarfs, which stars are the giants. It's not obvious just looking at them, but if you can figure out L and T, you got R. Now we know a third real physical thing. Now we're really getting off to the races. We now know 3 real properties of the stars. We know luminosity, we know temperature, and now we know radius. Awesome. Now we can start really doing the job of figuring out why are stars the way they are? How do they work? What are they? What's going on out there? Now we're really going to succeed. And we can take this even further, which will be the topic for another day. All right. Before we get to that, though, let's get a little bit more practice thinking about these things. So this is a little bit of a job, so give yourself plenty of time. The electromagnetic spectrum of light is 47 to 49. That's just dealing with the properties of light. Then jump over to 59, page 59 in the Green Book, and do the Blackbody radiation tutorial. Again, if you can work with a partner, please do. It's really going to help you and your partners if you can talk through this and help each other out. And turn them in when you're done. And if you have questions, ask Andrea or I. All right. Should take you about 30-35 minutes to do this. So you know how much time to block out for yourself. And then turn those in when you're done. All right. Have a great day, everybody. Bye.